The universe is a vast and mysterious place, stretching out in all directions, filled with countless stars and galaxies. It is full of wonder and beauty, with each star and galaxy telling its own unique story. One of the most awe-inspiring phenomena in the cosmos is the birth of stars, a process that takes place in the heart of glowing stellar nurseries. Stars are born in giant clouds of gas and dust called molecular clouds, which are the cradles of star formation. These clouds are cold and dark, and they can be light years across, spanning vast regions of space. Molecular clouds are mostly made up of hydrogen and helium, the two most abundant elements in the universe, essential for star formation. They also contain trace amounts of other elements, such as oxygen, carbon, and nitrogen, which play crucial roles in the chemistry of space. These elements are the building blocks of planets and life itself, forming the foundation of everything we know. Over time, gravity begins to pull the gas and dust in a molecular cloud together, initiating the process of star formation. As the cloud collapses, it begins to spin faster and faster, conserving angular momentum. The spinning cloud flattens out into a disk shape, a structure that is crucial for the next stages of star and planet formation. This disk is called a protoplanetary disk, a region where new planets begin to take shape. Protoplanetary disks are where planets are born, evolving over millions of years to form complex planetary systems. In the next section, we will explore how these disks form and evolve, shedding light on the intricate processes that lead to the birth of new worlds.
Imagine a giant cloud of gas and dust, many light years across. This immense cloud is a cosmic nursery, a place where new stars are born. This is a molecular cloud, a stellar nursery where stars are born. These clouds are the birthplaces of stars, filled with the raw materials needed for star formation. Gravity is the driving force behind this process. It acts like a cosmic sculptor, pulling the gas and dust together. It pulls the gas and dust together, causing the cloud to collapse under its own weight. As the cloud collapses, it starts to spin. This rotation is a crucial part of the star formation process. Think of a figure skater pulling their arms in to spin faster. The same principle applies to the collapsing cloud. The cloud heats up as it collapses, with temperatures rising dramatically. The center becomes denser and hotter, forming a core that is the seed of a new star. This hot, dense core is a protostar. It's the early stage of a star's life. It's not a star yet, but it's on its way. Over time, it will continue to evolve and change. The protostar continues to grow, pulling in more gas and dust from the surrounding disk. This accumulation of material is essential for its development. This process of collapse and spin is fundamental to star formation. Without it, stars as we know them wouldn't exist. It also sets the stage for the formation of planets around the newborn star. These planets form from the leftover material in the surrounding disk, creating entire solar systems.
As the protostar grows, the surrounding material doesn't just fall directly onto it. Instead, it forms a swirling disk. This disk is called a protoplanetary disk. Why a disk? Imagine you're looking down on a spinning top. Anything thrown onto it will be flung outwards. The same principle applies to the collapsing cloud. The spinning motion creates centrifugal force. This force acts outwards, pushing material away from the axis of rotation. The result is a flattened disk of gas and dust. This protoplanetary disk is where the magic of planet formation happens. Over millions of years, this disk will transform into a planetary system.
Deep within the protoplanetary disk, the protostar continues to grow. It pulls in more and more gas and dust from the surrounding disk. As it gains mass, its core becomes even hotter and denser. Eventually, the temperature and pressure in the core becomes so extreme that something amazing happens. Nuclear fusion begins. Hydrogen atoms fuse together to form helium, releasing enormous amounts of energy. This is the moment a protostar transforms into a true star. The star ignites, bathing its surroundings in light and heat. This event has a profound impact on the surrounding protoplanetary disk.
Section 5. A disk of diversity. Temperatures and composition. The protoplanetary disk is not uniform. It has a distinct structure and composition that varies with distance from the star. Close to the star, temperatures are high. The intense heat vaporizes most of the volatile materials, leaving behind mostly rocky material. This is the inner region of the disk. Further out, temperatures are cooler. Ices, made of water, methane, and ammonia, can survive. This is the outer region of the disk. The composition of the disk plays a crucial role in the types of planets that form. The inner region favors the formation of rocky planets. The outer region is where gas giants and icy bodies are more likely to form.
Section 6. From Dust to Planets, the Planetesimal Theory. The protoplanetary disk is not just a swirling mass of gas, it's also filled with dust grains. These grains are tiny, but they're crucial for planet formation. Think of these dust grains as the building blocks of planets. Over time, these grains collide and stick together. This process is called accretion. As these clumps grow larger, they attract more and more material. They become planetesimals, small bodies that are the precursors to planets. These planetesimals are the seeds of planets. They will continue to grow and evolve, eventually forming the planets we see today.
Section 7. A Dance of Gravity, How Planets Form. Planetesimals, once formed, don't just sit still. They interact with each other through gravity. Some collisions are destructive, smashing planetesimals apart. Others are constructive, leading to further growth. Over millions of years, this gravitational dance sculpts the protoplanetary disk. Larger planetesimals, with their stronger gravity, attract smaller ones. This process, called gravitational accretion, leads to the formation of planets. The largest planetesimals become the cores of planets, while smaller ones become moons, or are scattered away. This process is a beautiful example of how order can emerge from chaos in the universe.
Section 8. Clearing the way, from protoplanetary disk to planetary system. This journey is a fascinating transformation that takes place over millions of years. As planets grow, they clear out the gas and dust in their orbital paths. This process is crucial for the development of a stable planetary system. They create gaps in the protoplanetary disk, which are essential for the planets to establish their orbits. This process is like a cosmic vacuum cleaner, tidying up the space around the star. The planets act as giant sweepers, ensuring their paths are clear. Eventually, most of the gas and dust in the disk is either accreted onto the star or incorporated into planets. This material is vital for the growth and formation of these celestial bodies. What's left behind is a much less dense disk. The thinning of the disk signifies the end of the chaotic early stages of planetary formation. This marks the transition from a protoplanetary disk to a planetary system. It's a pivotal moment in the life of a star system. The planets are no longer embedded in a thick disk of gas and dust. They have emerged into a more stable and clear environment. They now orbit the star in a much clearer environment, free from the dense material that once surrounded them. This transition is a significant milestone in the evolution of a star system. It marks the beginning of a new era where planets can thrive and develop further.
Section 9. Leftovers of creation. Debris disks. Even after the planets have formed, some leftover debris remains. This debris consists of small rocky and icy bodies, ranging in size from dust grains to boulders. These remnants form what's known as a debris disk. Debris disks are much fainter than protoplanetary disks. They are also much less massive. However, they can still provide valuable insights into the history of planetary system formation. By studying debris disks, astronomers can learn about the composition and dynamics of the original protoplanetary disk. This can help us understand how our own solar system formed. Section 10. Seeds of life. Organic molecules in protoplanetary disks. Protoplanetary disks are not just factories for planets. They are also where the building blocks of life can form. Astronomers have detected complex organic molecules in these disks. These molecules, such as water, methane, and even simple sugars, are essential for life as we know it. Their presence in protoplanetary disks suggests that the ingredients for life may be common throughout the universe. This discovery has profound implications for the search for life beyond Earth. It suggests that the conditions necessary for life may be widespread.
Section 11. Looking ahead. The future of protoplanetary disk research. Protoplanetary disks are fascinating objects that hold the key to understanding the formation of planets and the potential for life beyond Earth. As telescopes and observational techniques continue to improve, astronomers are making incredible discoveries about these disks. With new instruments, we can study the composition, structure, and evolution of protoplanetary disks in greater detail than ever before. These observations are helping us refine our theories of planet formation and the origins of life. The study of protoplanetary disks is a vibrant and exciting field of research. As we continue to explore these cosmic nurseries, we are sure to make even more amazing discoveries about the universe and our place in it.